and we'll get the current that flows through here. And that current, as it flows through a body that has a change of conductivity, there's going to be charges that are set up. And we could measure what those potentials are by doing this across a whole line of data. We'd have a whole bunch of numbers that we could convert to apparent resistivities, and we could take those numbers and invert them, and we'd get out a conductivity or a resistivity model. Okay. Then we did a following experiment. We said, okay, let's suppose we have a different kind of source. We have a transmitter up here, and this is an inductive source. And that's going to generate, with time varying magnetic field, produces an electromotive force, E field, and that generates currents that are going to flow in here. So those are induced currents. This is a galvanic experiment. And we call these galvanic currents. This is an inductive experiment. These are induced currents. So both of these provide some way of discovering the body. This, however, only works if the material is conductive. You're not going to find a resistive body, or at least not very easily. So those are two different sort of thought processes. They're very different on how we ignite the body. Notice in this one, there's no charges. No charges that are built up. In here, that's all there's no circular currents that are going on in there. So they're very, very different ways physically of getting them. Then we thought, look, if this works and this works, why don't we combine them? So now let's do the following. Got something that looks like this, and now we're going to have current. But this current here is going to be a time varying current. So it's either going to be something, then that looks like this, or maybe it's in the frequency domain, it's a harmonic current. So this could give us the best of both worlds, right? We could have charges that are going in here, and we could also have induced currents. So we could have both galvanic currents, we could have vortex currents, we might have everything. So potentially this might be the best way of trying to do this. So that's fine. So that was DC resistivity. This was induced. What do we call it? And these were grounded sources. So that was actually 3 days with that respect. In a way, that can give rise to everything you need, but there's practical limitations. When we work with this, what's the limitation on how deep we can see if we started to talk about depth of investigation?
The skin that?
Pardon me?
The skin that?
In this one here?
In this one,
Yeah, so if this was the biggest length of our electrode, and it could actually be, it works kind of the same if this is your current source and here's your farthest electrode. So that'd be the kind of the same thing as in the stream code. Your depth of penetration, is maybe L upon 3 or something. And that's a really approximate number, right? So it just puts you kind of in the right ballpark, but after that you've got to look more. this guy here, what's the thing that is important from the point of view of, if you thought about depth of penetration? Pardon me? If we have a time domain function we set off of a pulse, then we have that diffusion distance. So the latest time that you have gives you that biggest diffusion distance. And if we had a frequency domain system, in depth, it was 500 root rho upon. So those are two things that tell you how far the waves go in. But then there's also a question here about how much energy you could put in. I mean, in a way, you could say, well, why don't you just keep measuring? So let's just do measurements at greater and greater time. You could do that, but the strength of the signal decays away because your source is effectively a dipole source. And remember, so you've got something that's way down in here. The fields drop off there as one of our cubes. So there's a geometric decay as well as an exponential decay caused because. So then when we look at grounded sources here, we see that the good news is that we've got kind of the best of both worlds. We're probably exciting the body in a better way than we do with either of these guys independently. And at the same time, we're still going to be limited to the kind of the same general depths of investigations. Something's going to depend upon how large this current electrode is, as well as the times that we're going. The bottom line with these kind of surface measurements is it's very challenging to see deeper than 500 or maybe 1,000 meters. To increase that, to increase the penetration depth to actually make currents at some particular time larger, what's the critical thing that is involved? I mean, suppose that you've got a transmitter that's sitting up here, and you want to see deeper. So see deeper means you need to have more power. What's the term that's kind of relevant to power in these cases?
The moment, the area times the current.
Right. So it's your moment that you have, which is the current times the area. So somehow, if you can make that bigger, you're going to see deeper, and you can do that by increasing the current or increasing the area, or in some cases, you might have an and loops. Just make a whole bunch of loops, and then you actually. So there's certain things that you can do to try to see deeper, but the bottom line is that if you're sitting at the surface of the Earth, you've got these kinds of systems, it's challenging to see really deep. So that's the motivation for this morning for looking at something called natural sources. So let us go through that. So here's our motivation. Suppose you've got big things that you're looking for. So maybe you're trying to understand what the structure is underneath a volcano. Maybe you're trying to find the base of salt in hydro problems or in sort of hydrocarbon problems. Maybe you got big geothermal systems out here, groundwater, maybe mineral targets. So sometimes you have these porphyry deposits. These guys are 10 kilometers on a side, or maybe even have stuff at a continental scale where this is hundreds of kilometers or thousands. So the big thing here is designing an experiment that you can pump enough energy into the ground to excite what is going on at depth and therefore obtain a signal that might be indicative of what's there. So this is kind of a continuation about what I was just saying. Ordinarily, this is what we have. We've got some kind of a transmitter. It's a loop of wire. It's got a particular area. And the fields fall off from that geometrically. So there's a 1 over r cubed fall off. That's just geometry. And then if you get currents in here, they're going to fall off as 1 over r cubed to the receiver. So total, that's 1 over r to the 6, the total geometric decay. And that's really big. A factor of 2 in distance gives you a factor of 32 in amplitude. 64. Okay. So what we really want to have, I mean, in order to make this bigger, we need to have a bigger moment. Right? So how can we do that? Well, suppose that we, instead of a transmitter that looked like that, we actually had a transmitter that was really big. So up in the sky, we got something that's, let's say, a couple hundred kilometers on the side, and now that would be a big transmitter, and that would provide in the center of that loop effectively a plane wave that's coming down. And so now there's no geometric loss for that plane wave. So the plane wave moves down, hits this target, and now we still have a 1 over r cubed fall off for energy going back, but we've at least excited the target. So that's the motivating idea. That's now, okay, well, we'd like to have that. How do we get a plane wave that is of that magnitude? Well, we can't design one, of course, but Mother Nature does provide such a thing. We've got the sun, and here's our Earth. It's not scale, of course, but what you're seeing here are lines that are coming out. These are particles kind of constantly spewed from the sun. It's interacting with the Earth. This is the Earth, and here is our magnetosphere that's going around. It's getting blown back by this solar wind, so that if you looked from space at what the Earth's magnetic field looks like, it kind of looks like that. We're sitting down on the surface of the Earth, and it actually looks kind of like a big dipole, but later on, if you go out, it's a bit distorted. This is a very active system. It's constantly changing, and sometimes there's big storms there. Has anybody here either seen Southern Lights or Northern Lights aurora? Yeah. Where did you see it?
Tromsø, in northern Norway.
Okay, yeah. Want to describe what you saw?
Yeah. I have a photo is the screen.
Oh, nice.
What I took.
Yeah, it's good. I don't even.
Tu tirou essa foto?
Vai ser Google Aurora capture screen. I know. I have one of these.
I have no.
Yeah, it's pretty dramatic.
I did a time lapse video also.
Oh, really? Nice. So what's causing that, of course, are particles that get funneled down Earth's magnetic field lines, and then they interact with ions in the upper atmosphere, put to an excited state, and when those decay down, they give rise to lights. There's something called the auroral electrojet. That is a concentration of where those currents are, and if you're up in that northern hemisphere just about every night of the year, you're going to see these kind of shimmering lights, and they're actually pretty amazing. The other thing that we have is lightning strikes, and Brazil is blessed with these guys because you have all kinds of them. And the thing about both of these is that these are currents. So these are time-varying currents. Time-varying currents give rise to magnetic fields, which vary with time. So we can see that, maybe there's the potential for using these guys as sources for my geophysical experiment. And that's exactly what natural source electromagnetics is. So I've got a movie, just to kind of show you what happens.
I have a question.
Yep.
What about the ionosphere currents?
The currents that we're actually seeing are from the aurora are in actually the ionosphere.
Ionosphere, okay.
Yeah. The lightning strikes, of course, are between the ionosphere and back here. One place on here. There's a cursor. My cursor go. Huh.
You can click anywhere.
Yeah, but I lost my cursor entirely.
There it is.
Still lost it. Where'd it go? Oh, I see it there. I can't see it. That's okay. I can't see it on my. Why can't I see it on my screen? That's weird. Oh, how annoying. I should have prepped you on this. Yeah, I know, but why can't I see it on my screen? Okay. Okay, so let me tell you. I should have prepped you on this before. Here's what you saw, and then we're going to see it again. So here's the sun. The sun is very active, has solar storms, produce flares of all kinds of energy, and those actually have important consequences on Earth, because sometimes these big solar storms will cause huge time-varying magnetic fields. If you've got a power grid, for instance, you can get induced currents in that power grid, and it can blow out transformers and cause blackouts. We had that in the United States in the 90s. It just wiped out the whole eastern seaboard. So there's actually a major section of geophysics which is looking at natural hazards that come from this. Look at GIC. And so it's a very active area of research. Here you had some kind of of a disruption. Here's the Earth. Here's our magnetic field coming like this, and then it. So first of all, the predominant solar wind blows things back, so the Earth's field kind of tends to look like that. And now you get particles that are coming out from the sun, and they actually interact with this Earth magnetic field. This field of the Earth is what protects us from all of this ionizing radiation from the sun. Without this protective sheet, there wouldn't be life on Earth. So this magnetic field is the thing that saves us. In this particular case, the particles kind of blow around like this. And then there's an interesting phenomena that happens at the back end. You get something called field line reconnections, and these particles that are kind of blowing back get trapped in, and there's field lines that get connected, and then the particles move back in this way. So really things come in, they come in from the back end, and then once these particles come in, then they just spiral down these field lines up into the ionosphere, and then that's where they're causing the aurora. So that was basically what you saw in this movie. I'm going to play it again so that now you have context. Huh. You can tell I wouldn't be very good at video games. Can't be that hard. So it's just about ready to go. So now we have the flash. So there's the particles going out. So now there's a bit of a time lapse. Those things could take a day or two to.
This is a helium blast or only radiation?
No, these are actually particles that are coming out. I do. This is ridiculous. Okay, just tell me when to stop. Okay. Okay, so now we got a good drive. So the particles come out here. Right, so now they go down. Okay, so now here's the Earth's field. So the particles could come in, they go blow it around, right? And then there's this interesting process of field line reconnection. So the fields here just kind of, okay, stop. And then, so now you can see, so here's the particles, they're sort of funneling back in around field lines, and they're going to funnel back in and come back into the Earth's. Okay, stop. So everything is kind of symmetric around there. So here's, it's called the auroral oval. So particles are coming in and they're interacting and they're giving these northern lights up here. And then they decay. Thank you. So that's basically a procedure. We get a lot of signal from that. And if you're, if you're let's say in Petrobras, and if you're ever going to have some MT done, you'd actually be pretty concerned about what the overall activity is of the sun, because there are certain times the sun goes through cycles. There's a 14-year cycle. Sometimes it's more active than others. If there's low activity, sometimes you just simply can't collect these magnetometric data. So we not only have that solar activity, we also have lightning strikes, which come. And again, lightning strike is just charge moving, from the surface of the Earth up to the clouds and vice versa. And that gives rise to another time varying source. Turns out there's a lot of variations of magnetic fields. This is a spectrum. This is period of the wave. So I go from 10 to the minus 3 seconds to 10 to the 5th seconds. And this is basically the energy that is existing in the natural source, in the natural sources. And it's got this power spectrum then that looks like this. If we ever get energy into the Earth, so whether it's these auroral jets or whether it's a lightning strike, then that energy propagates out. But we do have, and Marcus was mentioning, so what about the ionosphere? The ionosphere is a region, it's about 100 to 400 kilometers up. It's ionized particles. As far as anything coming in, that really acts like a high conductor. And so if you get an electromagnetic wave that goes, if part of it goes up, hits the ionosphere, gets reflected back down. The Earth is also a conductor. So to first order, you get electromagnetic energy that sort of propagates from here to the ionosphere and keeps bouncing around. So it's kind of like a waveguide, and it's kept in. And then this actually allows, this is the thing that allows lightning strikes in Brazil, okay, to actually have an effect, allow us to help us do experiments that are way up north in North America. So what happens to this this wave? So now you've got this lightning strike, you've got this wave that comes in. If you go far enough away from the actual source, all the kind of geometry of the wave is removed, and effectively you've got a plane wave that's coming in. The thing about a plane wave is that so there's a wave coming in, and now just as in seismic, that wave interacts with the surface via Snell's law, and that wave is going to get refracted downward. So the wave comes in, gets refracted down. The wave number is given by this complex number that we saw yesterday, and in the quasi-static regime, this relationship here between the transmitted angle and the incident angle here is dependent upon this quantity here. If you put in the parameters for the Earth, the thing is the electrical conductivity of the Earth is really big, and what it means is that this wave effectively gets refracted vertically down. So this is what happens. Even a wave that's coming in at 89 degrees hits the Earth, and it goes practically vertically down. So you can almost think about if you're on the surface of the Earth and you're trying to think about these electromagnetic waves, then it's almost as if the wave is traveling vertically down, and that plane wave will have an electric field either in the horizontal direction, either in the X or the Y. Now we're back to things that we were talking about yesterday. So we got a plane wave that's coming in. So it's going to be governed by the skin depth. High frequencies like this are only going to propagate a short distance because you have small skin depth. Lower frequencies propagate larger. And again, as we were talking about yesterday, these waves, they're waves, but they only propagate in a fraction of the skin depth before they're toasted. So what's the difference then between controlled sources and natural sources? The good news about controlled sources, we know everything. Okay, we know where the wires are, we know where the receivers are, we know what the boundary conditions are, we've got everything we can mathematically model the signal exactly. Natural sources, well, we still know where the receivers are, but actually the sources are random in space, and they're also random in time. So just think about your lightning strikes in Brazil. One over there, So we don't know that. We can't keep track of all of those things. So what's going to happen is we're going to have to do this. We're going to have to take measurements from many different sources, even when you don't know where those sources are. We're just going to record for a long time and do some sort of averaging to try to get this figured out. So the two Maxwell's equations in the frequency domain are still the ones that we had yesterday. The quantity on the right-hand side is the source term. And we notice that both E and H are going to be dependent in the same way on the source term. If we double the source term, then E and H are going to be double. And if we move that source term away, E and H are still going to be affected in kind of a similar way. What that means is that we can get rid of the effects of the source by taking a ratio of. So that's probably, again, something that you do in seismic under certain circumstances. There's a thing that's unknown. You can take take a ratio of things, and that kind of gets rid of stuff that's associated with that source or with what's unknown. So we're actually able to write the electric field as a matrix Z. So this is the horizontal electric field, EX, EY. A matrix Z times the horizontal magnetic field. And this matrix is called an impedance matrix. And it's got four terms. And so it says basically EX is dependent, so if we multiply this out, is dependent upon HX, that term, and HY on this term. So this impedance matrix is going to be the thing that encapsulates the information about the electrical conductivity. There's a couple things that we need to take care of, and again, this has its analogies in seismic. If you have a shear wave, you can have an SV wave, or you can have an SH wave. Kind of depends upon the polarization. We have the same thing here. We have what's called a TE mode and a TM mode. In a TE mode, the electric field is parallel to the boundary. So the E and H are always perpendicular to each other. And so in this case, the E is parallel to the boundary, H will cross it. In the TM mode, H is parallel and E crosses the boundary. That's going to become important later on, because remember, whenever we had an electric field that was crossing a boundary, we ended up like, oh, this current, that means there's current's got to go through there, and that's going to mean there's charges that are going up. If we had a homogeneous half space, and we did the following experiment, we put out an electric field sensor, so we have two probes connected to a voltmeter, and we measure the magnetic field, and then we took the ratio of them. That's called the impedance. We can actually get the resistivity out of that by this formula here. So omega is the angular frequency, mu is magnetic permeability, square this guy, and that actually gives us the resistivity. And then there will be a phase that's associated, and that is just given by this formula here. And in homogeneous medium, that phase is pi by 4. So again, this is, I find these things rather amazing sometimes. Imagine you got a plane wave that's coming down, and you really don't know anything about it. There's a plane wave coming down. And you've got a homogeneous Earth, and you measure the electric field, you measure the magnetic field, you take the ratio, you divide by some frequency, and the number that you get out is actually the resistivity of the Earth. So it's a way of kind of converting that kind of wave information into something that's really very tangible. In one dimension, we can think of them doing a sounding. So we've got the idea of skin depth, so no problem there. And I could imagine doing a sounding by having a frequency that's search flow really very high, right? So maybe I just see the first row, I see Marcus and Sergio, but then I use a lower frequency, I get back to Roberto, and a lower frequency yet, I get back to Luis, and so I could, if I had a suite of frequencies here, I could kind of do a sounding experiment. So that's what it is. Here's, let's say, 3 layers up here. So there's 100 ohm meters, 10, and 500. So imagine that we do, yeah.
The resistivity of a layer
we assume that this resistivity is independent on the frequency, right? It's a property of the material that doesn't depend on the frequency.
Correct.
So when we look at this apparent resistivity, when we have a explicit frequency terms in there, is that because the impedance itself also has an omega that will cancel, or it's just that for each different frequency, we are going to see a different depth, so the apparent resistivity does depend on the frequency, but the resistivity of each layer itself does not depend. I don't know if I
Yeah, no, that was
made
good.
myself
That was good enough. Maybe
clear. The point is that we have a frequency term in the resistivity, but the resistivity itself should not depend on frequency.
correct. Okay. So so suppose I've got a resistivity here, it's just constant.
Okay.
Okay. Oh, wrong knob. Okay. And now I've got a high frequency that's coming in. Okay. And so now here,
Okay.
that's all I get. Doesn't matter. I record the electric field, okay, and I record magnetic field, so I'll call it EX, HY. Yeah, they're the orthogonal ones. And so I take this number, okay, whatever electric field I've got, whatever magnetic field I've got, and I put it into that formula, and I have to know what frequency it is, right? So I divide by the frequency, and then I do EX upon HY squared. I do that, and I get.
Okay. So this ratio itself does depend on the frequency. Then when you divide, you cancel that dependency.
That's right. So the formula depends upon frequency. And then if I have a large wavelength, so now I'm seeing in deeper, right? So I'm actually sensing in deeper, but in this case, it's still the same resistivity. And so I do that, I'm also going to get broken off. What we're going to see now in doing the sounding is, let's suppose I had an Earth that was row 1, and this was row 2. Now, if I do the same experiment and I plot, now I'm going to use it just the same as we did before. Instead of having this as an absolute, like we say, oh, that's my apparent resistivity. That's like the resistivity of a homogeneous half space that would give rise to the same data. Okay? So now if I plot my apparent resistivity, and if I plot as a function, if I can plot it as a period, helps. Because then the left-hand side is the surface that we're going down.
Okay.
This way. So at high frequencies or small periods, I'm going to get something that's really connected with row 1. So it's going to be here, this guy's going to be row 1. And for a longer period, I'm going to get, so let's suppose this is 10 ohms. So this is here. And maybe this is 100. Okay. So 10, 100, at really high frequencies, I'm going to get something up in here, 10. A little bit longer, at lower frequencies, longer period, I'm starting now to sense this part in here. So I'm going to go up a little bit here. And at very long periods, so hard to draw. At really, really long periods, I'm going to come back up to, it's not going to be very much effect by that. So this is going to give me an apparent resistivity curve. So I'm looking here at frequencies or periods. And the high frequencies are going to sample the near surface, the low frequencies are going to sample deeper, and then So this is like an empty sounding curve. And it's really the same physical principles we saw with DC. Remember, kind of closed in, just like up here, up there. So it's very, very simple. So if I have this 100, a 10, and 500, so put frequencies, so the high frequencies are at the left-hand side because that's where we're seeing the shallow. So this is like the Earth's surface. And if I plot the apparent resistivity, we start off at 100, and then at some point here we are affected by this 10 ohmmeters, so it dips down. And then later on we get 500 because we're now just sampling the whole thing, right? So this is like an empty sounding curve that would be obtained. And it also has associated with a phase. Phase is not, you can't look at phase and kind of directly figure out what's happening, but it actually conveys information about that electrical resistivity. This impedance tensor that I was talking about before has 4 terms. In the case that it's 1D, the diagonal terms are 0, and the off-diagonal terms are the same amplitude, but they differ. One is the negative of the other. So Zxy is equal to minus Cy. That's it. That's in 1D. We have an app that you can explore things. It shows you what the apparent resistivities and phases are as a function of time. And also it's kind of nice, it illustrates what the, how the waves are that are coming in, what they look like outside, and then how they're attenuating as they go in. So I'm not going to show you that right now, but it's out there, and hopefully you can explore it, or maybe we'll do that a little bit later. So what happens in 2D? So now things get a bit more interesting. Let's suppose that we had a situation that looked like this. So we had 100 ohmmeters on this side and 10 ohmmeters on that side. We're going to do a survey that goes from left to the right. And we have 2 modes that could occur. There is a TE mode in which the electric field is parallel to the structure. And let's kind of see what happens with that. So if we're over on the left-hand side, we're going to measure out here. We're basically measuring over a region that's 100 ohm meters. We do the apparent resistivity out here. It's 100 ohm meters, so that's kind of nice. And as we go to the right-hand side for 10 ohm meters, it drops down to 10, and in between it has a smooth variation. Okay, so that's nice. We've got 2 units here. Do the apparent resistivity. Changes nicely from one asymptote to the other. The interesting thing about magnetic flux, or electromagnetic, is that it actually depends upon the polarization. So imagine, I'm not going to show you the slide at this point, but imagine what would happen if we had the other polarization. And the electric field was in this direction, in the x direction, and the y component was parallel. So first of all, now we've got a current that is going in this direction, and what's going to happen? What's going to be the effect of that on the electric field? What might we expect?
The current will somehow feels this resistive contrast.
Yeah, in the,
Yes.
and if I want to put a current through something, then the current has to be continuous, right? So whatever current is going in is going to be the same as the current that's going out. Okay? That's
So
good.
in that, yeah. So since there's a equivalent resistance of kind of average of the two mediums, right?
So what would you expect that if we plotted the electric field, then Austin, what would you expect?
If the electric field should be decreased, right? This is the resistance. The sigma times electric field should be constant, right?
Mhm.
So yeah, if the and sigma is the inverse of the resistance. Yeah, I should expect that the electric field will decrease as we go to the right.
Yeah, so the electric constant current means that, yeah, the electric field at this point is going to be different than the electric field.
Yes.
Right. Anything else that might? So, and do you think it's going to be like a smooth gradation? Jaja? What's going to happen?
So because of the resistivity contrast and the current, the electrical field will encounter that contrast interface, and there will be charges built up. So I would expect like a discontinuity in the electrical field.
Good. So we're trying to get a constant current through there. The current, there's going to be a discontinuity in that electric field right at the boundary, because on this side, okay, the electric field has to be large. This side has to be smaller. So there's actually a discontinuous change in the electric field right at that boundary. So there's a lot of charges now that are built up on that boundary. And the apparent resistivity, rather than being something that was kind of smoothly varying as it was for the other mode, stays up at 100, almost right up to that discontinuity, and then goes jump, and then almost is the value of 10 on the right-hand side. So things are starting to get a little bit more complicated here in the sense that we now have two modes that are going in, and if you're sitting, if you're sitting at a particular location and you've got current source that's over here and current source that's over there, you can appreciate that I've got electric field sources that are coming in this way, and then depending upon my structure, I might get charges that are built up, or I might get currents that are just kind of flowing along. Like, it might not be simple, and it might need to have some thought on how to unravel all this. I did make a comment. In 2D then, we've got an impedance tensor. It's got 4 values. The diagonal elements are 0, but the off-diagonal elements are no longer equal to each other. In 1D, those two things were equal except for a minus sign. Here, they could be quite different. In 3D, now things really start to get complicated. All 4 elements of the impedance tensor are active. There's no special symmetry, no special conditions. It's just a big 3D problem. So what about measuring, and how do we actually get to these impedance values, just to give you some sense about what's going on? So you're going to go out in the field, you're going to measure these electric and the magnetic field. So here's an EX, BY, BX, BY. And then also you generally tend to measure something at a remote reference station. So the horizontal components of the magnetic field. And then there's a set of processing that is required. You need to go from these time domain measurements to impedances, have information as a function of frequency. Here, as we have traveled around the world, there's all kinds of people that are attempting to do this. There's a number of codes out there that people are working on. One of our missions with respect to the SIMPEG initiative is to take something like this and have it open sourced so that people could look at the code and maybe contribute to it, you at least use it, and use that to help promote a community, because everybody around the world is trying to do the same thing. Some people they're using different codes, but often they don't know what's exactly in those codes, and then there's little black parameters that they're not sure about. So here's one of the specific areas that the SIMPEG community is kind of using as an example of how to connect. One way of thinking about how the problem works, however, is you got this big long time series. You can divide it into a whole bunch of windows. And somehow we have to go from time to frequency, which means we need to do what? How do we go from time to frequency?
Fourier transform.
Yeah, so we're going to do a Fourier transform. So we take these.
Question?
Yeah.
So why do we divide them into different time windows? Why not just do the Fourier transform using all the data?
Because we have many different sources that are coming. We don't know where those sources are. So it's like we're doing many different experiments. So that the way we're going to treat this is kind of do the processing so that on average, if there's an electric field in the x direction here, then I'm going to get this kind of a magnetic field, to kind of find that relationship between an electric and magnetic field. And in order to do that, we're just going to do statistical ensemble averaging. So we're going to do like many different representations, and then we're going to do a bulk averaging, and then use that to get an impedance function.
So you were to average over different time windows, so you get like from each time window you do the Fourier transform and you get an analysis and get a result, and then you kind of average the results from all those different time windows.
Yeah, that's pretty close. So we take one of these little time windows and we do a Fourier transform on that, we get an EX, and then we do Fourier transform on the same time window for H, and we get HY. Okay. Now we could just go ahead and say, okay, let's do EX upon HY, because that's the impedance, right? So we could do EX upon HY at that frequency, and that gives us an estimate of Z of XY. And then we could do one over the next time window do it for here, do it for here, do it for here, and then just simply do an averaging of that, right?
So the different time window does not really refer to the distance from the source.
No, we have no concept about where that source is coming. We're thinking that the sources are far away. They're basically plane waves coming in. We have no idea exactly where they are or what direction they're coming in at. So that's what we could do. So we have this long time series. So this is EX, and here's HY. And now we divide this into a block like this, and we do the Fourier transform here, so we get EX of omega. And let's call that 1. And here's HY of omega, call that 1. And we could do like ZXY is equal to EX1 divided by HY. We could do that. That would be an estimate of the impedance. No problem there. And then we could go ahead and do this again over here and again over here. And then now we could have something like an average ZXY, which would be sort of the sum I equal 1 to n of these guys. This would just do the average and divide by n. And so now we could get an average impedance. Okay, that's also a reasonable thing to do. Turns out it's more stable if you do one kind of modification. So instead of taking that ensemble average of EX upon HY, we actually use a remote station. And that remote station might have noise characteristics that are different from local characteristics. Because what you're really worried about here is local noise contaminating both EX and HY, and that would give you a biased estimate. So a less biased estimate is if we do the following thing: we take an H from this remote reference, take its complex conjugate, multiply that in, and do the same on the top and the bottom. Okay, and now we're going to basically average that. So that's going to give us. That's going to get started. Yeah.
So one more question. What's the frequency that you? So when you do the Fourier transform, you will get different frequencies. Right?
Correct.
So which frequency you're going to use for this calculation, or you calculate at different frequencies?
So here's where you have your options. So let's suppose that you are you're recording here. And this recording might go on, for 0 to, I don't know, let's say 1,000 seconds. So let's suppose it goes from 0 to 1,000 seconds. You want to be able to get periods that are as big as you or frequencies that are as low as you possibly can. On the other hand, you're going to want to have a number of these estimates so that you've got some kind of an average. So in this case, let's suppose you wanted to do an average of at least 10. Then you could take time series that were each 100 seconds, 1 to 100 seconds, and you could go ahead and you could take the Fourier transform of that, and that would give you something that goes from that nice frequency up to sort of period 100, and then proceed on. So the limiting thing is sort of the length of time that you're recording, and the fact that you need to have a certain number of repetitions. So by doing this, and certainly it's, the higher the frequency that you go, the easier the whole thing is, right? Because now you just get better estimates and you get, better ensemble averaging. What the trade-off is that generally you want to see deeper, right? Okay, so you want to see deep, you want to see down to 1 kilometer, right? So now you have to think about, okay, what's my skin depth? Okay, so suppose I've got some estimate of my background resistivity. So now I've got a skin depth of something that I want to work with. So what frequencies do I need to get down there? If that frequency is, let's say, 0.1 hertz, so let's suppose the frequency is equal to 1/10 of hertz, okay, then you need to have a time series that's long enough, so that's period of 10 seconds. You need to have a time series that's 10 times 10 seconds to get there. If in some cases, what you really want to do is to have periods of hours, okay, you really want to see deep, you're going to see the base of the basalt, okay, then you might need to go up to periods that are a couple hundred or a couple hundred minutes or something like this to make sure that you actually get down to those depths and have enough repetition to do that. That means that the equipment has to stay out longer. If the equipment is sitting on the ocean floor, then that's not such a big issue. But if you're on land, then you're having to wait there until you've got 10 of these periods that are coming in, and then you also have to look at the sort of the fluctuations that you're seeing as you're doing that averaging to kind of make sure that those averages are kind of converging down to something that's sensible, and then you can pick up and go.
So,
but they're
one more question.
yeah, no, good.
So when you kind of measure this using your receiver, definitely it's not a continuous measurement. So you kind of have sample by kind of a sampling frequency, right?
Yes.
Recording frequency. Does it have anything your sampling frequency? Does it have an impact on analysis?
Well, there's a Nyquist frequency that you're going to be involved with, but you want to it's really your highest frequency that you're concerned about here for the sampling rate. So you want to make sure that your sampling rate, that your Nyquist frequency, okay, is well above the highest frequency that you want, so that you've got a good sample. So at the high frequency, yes, that sampling rate is important. At the low frequencies, you don't need to sample so often, but you need to have a long length of time.
So I just try to understand one more thing. So when you say you kind of average them, so there won't be a time lapse in the process. So basically it's all like for each time window, you always kind of assume that's like from time zero. So
yeah, for each, that's right. For each of these guys, you're going to say, okay, here's 0 to some t, and then you start this one, here's 0 to some t, and then just keep going. So you're just treating them as like, okay, individual records. Like here's a record. And then when you go to longer periods, okay, so by dividing it in like this, for here to give you a suite of frequencies, if you want to go for a longer period, you might take a longer time window and then another one and another one, and kind of cascade down. Okay. Okay, so that takes us through collecting the data, processing the data, and now what are we going to do for inverting? So the difference between the control source that we've been talking about thus far and MT, some things are no different, right? We're still going to have a mesh, and we're still going to solve Maxwell's equations on the mesh. The biggest challenge with magnetotellurics, though, is that we really don't know what the boundary conditions are. In a control source, we do. We just go up far enough, but everything's 0, right? But in MT, you've got this issue of scales. You've got oceans out there that could channel currents in, and you've got different kinds of scales. You might be interested in something that's only happening in a 20 kilometer by 20 kilometer area, and your mesh that you're going to work with has to be much greater than that. And even at that point, you're not really sure if there's actually currents that are kind of being channeled from the Atlantic Ocean to. So there is issues with respect to boundary conditions. I mean, people can handle them, but that is something to be thought of. But otherwise, the inversion of MT data is really just the same as CSE. So I've got a couple of case histories. So we got one for geothermal, one for minerals, and one for hydrocarbons. At least I'll walk you through a couple of these. The geothermal one is interesting, and the hydrocarbon ones are especially interesting. So let's see where we go. So let's look at geothermal energy. Here's the place that we're going to concentrate on is Iceland. So it's on the mid-Atlantic ridge, so things are being pulled away there, and lava's coming up. So it's an area that has a lot of geothermal potential energy. We're going to look at a place in southern Iceland. It's called Henket. There's sitting on the Atlantic ridge, as I say, and all these red dots in here, those are all areas of high temperature. And this area in here has been especially productive. It's sort of does 300 odd megawatt power generations through the geothermal power. So geothermal energy contributes a major amount of power to the Icelandic grid. Before we do any geophysical survey, we're going to try to look at the physical properties and the geologic structure and try to figure out what it is that we really want to find. Basic idea with geothermal energy is there's usually some hot rock that's coming up, okay, and then water is coming into the system, can circulate around. You can get different types of alteration units that are happening, and at the end, you could end up with something that looks like this. At the near surface, you just have near surface rocks. They could be quite resistant. And then as a reaction to this, these fluids that have been going on in here, there's an alteration, there's a clay alteration that happens. And this is a very low resistivity layer. Underneath that, there's this kind of resistive core, and deeper than that, there is a sort of hot magnet source. So as a first order approximation, that's kind of what you're looking for. And most geothermal the companies, when they're going out and looking, they're actually trying to find the bottom of this conductive layer up here, because that sort of indicates where you go from clay, which is non-permeable, to water in a reservoir here that you might be able to extract. In addition to that, in this particular example, as the water is coming up through here, it's heated, and there's sort of a higher temperature region in here, and that is actually going to cause the resistivity, which would have been more like 250 to 1,000 ohm meters in this background host. That makes that more a lower resistivity, so maybe 50 to 100 ohm meters. To look at this whole scenario now, we want to see if we can't find this overall structure, but in particular identify regions of low resistivity in this host part here beneath that conductive clay cap. So that's kind of the overall goal. Here's our cartoon model of what we think is there. We're going to do an MT survey over here and see if we can't find, first of all, this clay cap, and then maybe underneath it some regions of moderately high or moderately low resistivity. So what's the experiment? First of all, here's the survey. This is a company called Phoenix Geophysics, pioneered MT for many years. The survey measures magnetic fields that use coils. So here's the three coils, and then also measures electric field, so it needs probes, and that's what these guys are here, and then everything is kind of hooked up. In this survey, there was 133 stations that were put in, and the frequency band is about 300 hertz on the upper end and 0.001 hertz on the lower end. So that's 0.001 hertz, that's 1,000 seconds. And remember I said that, we're going to want to have a minimum of at least 10 of those. That's probably pretty conservative. So that means that you need to have 10,000 seconds of data that you're recording, which is larger than a day. Then there's a remote station. It was about 40 kilometers away from here. So if we look at the data, I'm going to concentrate on just three locations. There is along here at station number 1. Here's the apparent resistivity that's measured. So the red curves are the XY. So as you're measuring the data, so you've got electric field this way, and then magnetic field this way. So we can look at EX and HY, so that's one of them, that's the red, or we can look at EY over HX. Okay? And so if we look at the apparent resistivity curves, the red and the blue, so this is frequency along here, the red and the blue actually overlap in the early stages, so in the high frequency. So first of all, what is that telling us? So the fact that the red curves and the blue curves overlap. Yeah. Somebody comes along, I'm going to show you.
Like no preferential directions, like a homogeneous.
Perfect. Yeah. So doesn't matter whether they made it this way, doesn't matter whether that way, no preferential direction. So I'd be pretty confident in making an assumption that my apparent resistivity of the Earth is kind of looking like that. Things are pretty homogeneous. So it's like at least 1D.
It's in this part of the Earth, and then it's
right.
The curves.
Yeah, and as you go out this way, you go to progressively lower frequencies, and then you see, things are changing. Yeah, so they're separating, and then farther apart they separate. So there's 1D Earth maybe at the top, and then there's other stuff that's happening. And just from looking at the character here, it's resistive close to the surface. Gets lower resistivity, and then both these curves go up. So it's probably higher resistivity, then low, and then high. So just by looking at the apparent resistivity curves, you're at least like, okay, there's at least 3 or 4 different layers there, and then there's some lateral variation changing. So that's at location 1. You go to location 2, and look how much difference it is. So this was at 100, and this is down about a factor of 10 of that. So we've become much lower resistivity in this region in here. And also the curves have split right from the get-go. So that means that there's variation that's going in here. It's at least 2D. That said, we do reduce resistivity, then increase it, maybe reduce it again, and then increase it. So there's, at a first order glance, there are some things here that are still similar, but definitely changes between here. So now we want to take those data and invert them So we do that. So this is actually a major computational step to invert the magnetic or magnetocaloric data, because we've got multiple frequencies from 300 hertz to 1,000. And it's a big problem. So there's a couple million cells that are involved, and takes serious computing time. That said, here's the final answer. This is a cross section through that model, and red indicates conductive material, blue is resistive. And so see what you got. So first of all, we've got this red stuff here at the top. So that's what we're looking for. We're thinking, okay, there's this clay layer, the clay layer there. We expect things to be hot at the bottom, so it'll be conductive. And in between, in that kind of host region, we see it's kind of blue, but there's parts that have lower resistivity here and here. So that's looking pretty interesting. If we plot that in a slightly different manner, so that we kind of have a 3D volume, we've taken a chunk out and then done a volume rendering on the resistivity. There's a high resistivity section that's sort of kind of coming out of so that's another view. And again, here's your other view of the of that clay layer. So what's the interpretation here? Well, this the very top region that's in green, that's sort of our resistive rock. Microsoft is checking out, making sure I'm up to date. So we got our resistive rock at top, then we got our clay layer, got our conductor at depth, that's our heat source, and then we've got this resistive region in here, and then we've got two regions here that seem to have a lower resistivity that might correspond to that. So this image here actually has a lot of characteristics that are associated with this initial cartoon that we had portrayed. And now the thing is to okay, let's test this out. So our hypothesis that this lower resistivity region in here is corresponding to this, and maybe this low region here is also kind of corresponding to one of those reservoirs. So the idea then is okay, let's drill down in through here and see what we get. That was done, and here are the drill holes, and they're color-coded with temperature. So for instance, pick something in here, it's going down through here, and then you get into this kind of magenta color, sort of deep, rich reddish purple. And if you look at that temperature is 250, 300 degrees Celsius, and all of these wells in here are consistent. The same is true with over here. Going back into here, these wells indicate high temperature. So it's actually really pretty a pretty positive result that has come from the resistivity. There are a couple of wells that indicate still have high temperatures. They were drilled into this dark blue region. They did have high temperatures, but there was really low porosity in their permeability. So it was hot, but there was no water.
And did this well also measure the resistivity, so you could compare a hard data with the inversion?
No, those wells were just, they recorded temperature, so it would have been nice for that.
Yeah, it's in size it's very urgent. Yeah, just color the wells with the log impedance.
Oh, right.
And then you put in the same screen the inversion, so it's like a visual QC of the inversion.
Yeah. The part of the problems with logging these drill holes is also the sensitivity of your tools to
Yeah,
to
sure.
the temperature. These are pretty high temperatures.
Yes.
Can I have a question?
Yeah.
So in this case, basically, the MT is measured the resistivity. So how does the temperature, because I'm thinking about my case, when you have the steam injection in your heavy oil reservoir, and you have temperature between, let's say, 50 Celsius to like 300 Celsius, will that temperature difference cause enough difference in the resistivity that can be measured by the MT?
That's a good question. I don't know. In general, you increase the temperature, you're going to increase that conductivity. But again, how much that changes, depends so much on, rock type, what the fluids are that's going in, what salts are around, tons of questions. But. We do have a case history. It's a mineral deposit. It combines DC resistivity, Csa Mt. So the Csa Mt is something called control source audio magnetotellurics, and what it does, it's essentially a controlled source experiment. So here's our current. I'm trying to draw a plan view here. Here's our current source. If I go a long ways away, okay, so if I go, let's say 5 kilometers. So let's suppose this is a kilometer long. So if I go, let's say 5 or 10 kilometers away, I'm sitting over here. Effectively, the waves that are coming in here kind of look like a plane wave. There's no more circular geometry that's associated with that, and I can represent the waves that I've got here as being plane waves. And then once they're plane waves, then I can use the MT processing to go ahead. Because now I've got a wave that's coming in, polarized. The electric field is in this direction, magnetic field is in this direction. It's a plane wave is a plane wave. The fact that this one happened to be generated from something that I know compared to just some random lightning strike really doesn't affect things. So as long as you're sufficiently far away from the source, and we have an app that can help you kind of make that decision, then the signals that you're measuring are effectively MT signals, and then you can use MT processing in order to work with that. Yesterday, I showed you a case history from the hydrate ridge. This was the looking for methane hydrates. I guess I could. I'll just sketch it out. So there's sort of a Y and an X. And remember, there was 2 lines of marine CSEM data that were shown, and we had some permanent sensors on the bottom, had some MT sensors, so 3-component. So some of these were MT, and then some of the sensors then were also just towed on the ship. So there's permanent MT sensors, and also we had the ship line Yes. Yeah. So now they're they're towing this guy over here and over here, and they're using the ground MT measurements as well as these guys in the ship. But what was on that plot, but you didn't see it, was another line. I don't know, kind of like that, sort of. And labeled up here was a CSA MT. What this one was is they were towing this transmitter. They're still towing the same transmitter. They're towing this wire, and they're just moving it around up here. And then they're recording the fields on these MT sites, and then using that information to as MT signals, and then inverting that to also get some information about the electrical conductivity. So anytime that you're sufficiently far away from a source, then you can regard your signal that's coming in basically as being in that far field region, and you've got, like, you can use MT processing to help you out. So that's an important component. There'll be a little bit of that also in the case history that comes in with that Sadia talked about in just a minute. So this example kind of runs through a little bit of that, and I'll just, without kind of going into detail, I'll just kind of flip through to kind of quickly show what's going on. So this is a porphyry deposit in Chile. So it's sort of sitting right up here. It has gold-hosted deposits that are associated with it. A lot of hydrothermal circulation and alteration, and that's what's given rise to the mineralization. These porphyry systems have a kind of a characteristic generic kind of representation to them. They're sort of an inner core that is mineralized, and there's various types of alteration products that have gone on them. And then sometimes these things get eroded off, sometimes they get tilted. But the bottom line is that this guy here is kind of sitting up in that mountain. They first do ground magnetics and look to see where the magnetic susceptibility is. Some of these alterations occur and actually are magnetite destructive. So the alteration comes in, and if there was magnetite there, it gets rid of it. And that's a good sign, because this helps to kind of delineate what the alteration zone is like. And the initial discovery was done, first of all, on the basis of this sort of magnetite destruction zone, and then they're going to do a Csa Mt experiment to test to see if they could, just to see what they could find as far as the mineralization. So the properties that were used here are actually both. There's two things. One is resistivity and one is chargeability. We haven't got to the chargeability, so we could kind of return to this example, a little bit later too. But the host rock is really resistive. The stock has got moderate resistivity, and the alterations have very low resistivity. So that kind of is what's distinguishing them. And there's various parts of this region that we're interested in that kind of correspond with the genetic representation of a porphyry deposit. So here's the Csa Mt survey. We've got a source that's here, and we're just assuming that we're far enough away from the source that we're basically getting plane waves. And then once you've done that, just use the MT processing. And for this particular case, they had a 3 kilometer dipole, and they're about 10 meters or 10 kilometers away. So once you get to be, a number of scale lengths of the size of your transmitter away from that source, then you're in the kind of in the plane wave domain. Depends a little bit on the electrical resistivity, but that's sort of the idea. So the initial setups for the Csa Mt, so this is like empty data, and was the inversion. The red indicates low resistivity, so there's something in here that's really conductive. And the kind of the result of that was, from a take the Csa Mt data, invert it, do a cutoff for the conductivity, and you get a volume of material here, low resistivity, that sort of matches what the gold and the copper anomalies were, how they were recorded. So what they then did is they did a couple of drill holes, and they found that the mineralization actually extended beneath what was obtained from the Csa Mt data. So now the Csa Mt data, so I said it's like MT data, but there was a particular frequency band. And if you go to the lowest frequency, that gives you the deepest penetration, that's as far as you're going to get. And so those data were inverted, and they give an electrical resistivity up here, but the depth of penetration was only the skin depth was 300 meters. So that means that the Csa Mt is okay, but it's sort of just seeing the top few hundred meters. So we wanted to do something that was beyond that. So now you want to have something with a greater depth of penetration. The system that they have is something called the Orion System. So it does DC resistivity, IP, and it does MT. So in DC resistivity, we've seen what that is. Well, I think here we go. Here's the Orion System. Basically, you lay out a whole bunch of electrodes, and then you use these electrodes as you take pairs and use them as current transmitters, and then you measure use other pairs to get voltages. So here we had about 500 odd transmitters and 300 receiver dipoles. This is something that's probably pretty familiar to people who are doing seismic, right? So this is kind of like the equivalent of ray coverage in seismic. You got to have a lot of instruments, set them out, and then if you just do kind of like a pseudo section analysis, see where all of those intersection points are, then you can ask the question, okay, do I look at least at this crude level like I'm sampling the volume that I need to do? In addition to that, there was 100 MT sites that were there, data acquired overnight, and so during the daytime, they would use this system and do the DC experiment, but then you just leave the equipment run overnight, and then you just collect all this natural source field data, and then you process as MT. So that's kind of nice, right? You lay out some electrodes in the daytime, you have active sources that are going on, and you measure, and you're measuring the DC resistivity data, and at nighttime you're just leaving them there, and then you're measuring both the electric field and magnetic fields, and then you've got MT. So the DC data is 150,000 data. Yeah, can't really make much sense of that. That's sort of an apparent resistivity. But if you process and you invert, you get some kind of a volume that looks like that. And if you take a pie slice out of it, there's a high, well, a good conductor, low resistivity zone. And if you plot it up, it's got this kind of circular geometry to it. And that's kind of nice because these porphyries come up and then they've got, they're kind of axis symmetric. So the alteration that goes around is, you know, having something that goes around the ring is a good idea. And then that previous one was at 700 meters below sea level, below the surface, and this is at 900.
Yeah. So are all those results from inversion?
Yeah.
So basically, like in inversion, basically you need to have a model, and then you do forward modeling, and then you kind of minimize the error function to kind of finalize, get your resistivity distribution.
Mm-hmm. Yeah. So all the inversions that have done are sort of done in the same way, and we'll actually take you through that this afternoon. But you're always take an Earth, you know, a mathematical representation of an Earth model, divide it up into cells. Might be 1D, might be 2D, might be 3D, and you just got all of these cells that you're trying to find values for, and then you adjust the values of those cells through Gauss-Newton procedures to find a final solution that reproduces the data adequately and at the same time, you know, with something that's geologically useful.
Okay, so it always require kind of forward modeling, right?
Absolutely, yeah. You have that's a requirement at the outset that you need to be able to simulate the responses that you obtain with that survey layout for whatever resistivity structure you got. That's crucial. So we also have IP data. We haven't talked about IP data, so I'm not going to dwell on that. But we will get to the MT data. So here was 100 stations that were there, and we're going to invert those data. And when we do that, the MT data look like this. So there's a big conductor in there. And now we can compare it. So this, I think, is, there's some really interesting take-home messages here. So the first is, well, frankly, I mean, we've got 3 experiments that we're doing, try to find the electrical resistivity. Okay, so 3. And each of those has got its own ability to see at a particular depth. So the first was that DC Resistivity Survey, and that's basically seeing sort of the top level. There's a region of low resistivity in here, and it's seeing down that deep. When we do the MT on that, the good news is that we still got the MT result agrees with the DC in the upper regions, but the MT result also extends things down to greater depth. So in this case here, this is now, I think, a couple of kilometers in. And we also have the Csa Mt. When we plot that on, that's a little bit deeper than the DC. So the Csa Mt sees deeper than the DC, does not see as deep as the MT. But all of these are agreeing that in this region up here, they see a conductor, and some of them see shallower, some of them see deeper. And in fact, when they then went ahead and on the basis of the MT and the DC, put all that together, they had they spotted some drill holes, so they compared the resistivity with the drill hole results. So now they're actually logging what the mineralization is. So this is kind of contours in gold, and here's the isosurface at 10 meter level that's coming from the conductivity inversion.
It was not a joint inversion.
This was not a joint inversion. No. Yeah, independent. Okay, so I think there's a few important things there. So we did MT, so we kind of have an idea about that. And the good thing about MT is that, if you keep recording longer and longer, you just see deeper. There's a whole community of geophysicists who are really interested in deep structure and trying to get down into the well into the mantle, seeing the top 200, 300 kilometers down. You can do that with magnetotellurics. It just requires that you have stable instruments and that you measure data over very long time periods. But in principle, there's nothing to prevent you from getting really long periods and looking quite.
But when you look at very deep, you won't see like very high resolution.
Right, but at depth, I mean, maybe stuff that's 50 kilometers in thickness, that you've got some kind of a blob that's coming, like a 50-kilometer resolution, that might actually be pretty good. That's not very good if you're up at the surface, but at depth, to be able to look at a fraction, to have a resolution that's a fraction of the depth that you're looking at is what you can expect from electromagnetics. And sometimes that's good enough. So I'd like to, at this point, we'll just turn it over to Sagio, give you one, take you through this case history for the Red Sea, and then we'll have a coffee.
Yeah, so I'm going to introduce one case history called Red Sea. It's a research done by Colombo et al. So his name is Daniello Colombo, working at Saudi Aramco. Yes, and I think that this was the biggest marine EM survey and MT so far. I think it's what was done survey was done in 2011. So yeah, that's sort of the. And here's our setup. So it is located at Red Sea from Saudi Arabia. And the main geology here, actually I don't know that much about the exact geology, so probably you guys know more than me. So yeah, just let me know if you guys have any a comment. Oh, that's not true. And they it says basically a salt related geology, and that makes a lot of challenges. So here, the main geological unit is this layered evaporate sequences and the halite. So this part is the main challenge for the seismic, because I got some halite at high velocity, and this is the class bit where you got a sediment and low velocity. So they do have a lot of lateral changes in terms of velocity, which actually generates a lot of challenges for seismic, and that's where you got a basement. So basement itself has also pretty complicated geometry. So I think from the paper, what they said is it's quite different from Houston, Gulf of Mexico, which have a fairly simple salt domes. So here they got much complicated geometry, and this in the LAS or below. That's they got this class 6 or sediment. That's where they got the potential reservoir. So that's their target, and that's the setup. And yeah, it's basically that's kind of geology. That's what I've said, and they kind of classified as a couple of several layers. The POES is post evaporate sediment. And then that's where you got your evaporate sediment sequences. including both halite and the clastics sediment. And then below you got pre-evaporate sediment, which is another clastic sediment. And then you got the basement. So those are sort of like a simplified setup. And then it's pretty deep. It's about 10 kilometers here. And the thickness of the LES above around 5 kilometers. And the goals of the survey was, well, I think they probably want to find an oil. That's probably the goal. But in terms of the CSCM survey, I think they want to use MT and the CSCM survey to like help the challenges in seismic imaging. Remember that halite and the LES also generates the challenges for seismic imaging because of the lateral velocity changes. I think that was the main challenge, and they want to use both MT and CSCM method to help those challenges. I think that was the main thing. And also they did the gravity survey to map out the basement. And here at the end, we're going to compare the CSCM reserve with the basement and also with the seismic. So I think it's using the multi-physics. So you're really narrowing down the structures.
I have a question. Aim to better constrain the migration results is in the sense of the velocity model building?
I think so. I think they haven't, like in this paper, they haven't got it to that point, but I think that was the main motivation. So I think you're getting the good velocity model. I think that's the essential part of the high quality migration.
Resistivity derivative velocity model.
I think that probably they were imagining the similar strategy what Doug showed for Wadi Saba. Remember, they actually started from use the resistivity and topography conversion together, right? Increase the resolution for both, and then use that velocity to get the better migration. So that was kind of like a generic strategy, and that's what they're are aiming for. But although I think they didn't do that here. Okay. So here we're going to focus on the inversions of MT and the CSCM data and compare them with the seismic reserve and also the gravity inversion reserve. So that's sort of the holistic view of this case history. And here's our properties. So I think here the important unit is this guy first, LES. It's a little bit confusing because LES kind of contains both halite and the clastics. And I think in general that's the evaporate, so it has got greater resistivity than the other. So like sediment has a resistivity of 0.5 or 1.5. That's the background is quite conductive compared to LES. But in the LES, you got basalt domes, which is halite, and that's actually up to 10 to the 4 ohm meters, which is quite resistant. So in the sense of comparing halite and the clastics in the LES unit, this one is more conductive than that guy. Okay? And that's what we want to distinguish, either with the CSCM or MT. And the other interesting unit is the basement, which is quite thin. And it is resistive and high velocity. Okay? So I think usually our target has high velocity and high resistivity. Halite has a high velocity and high resistance. So those are, like I said, we got pretty good correlation here. So high velocity, high resistance. That's sort of what we're interested in. Okay. And the other thing, we got anisotropy in most of the sediment layer. So POES anisotropy 1.5. So we got the greater vertical resistivity compared to horizontal. Okay. And then here the resistivity stands for the horizontal resistivity. That's sort of the reference. And before they do a survey, it's a huge survey. So I think that's probably what you guys want to do as well. Like before you're doing the survey, okay, here's my geological setup. I want to do some simulation and some synthetic inversion on what kind of model that I can recover from the synthetic data. So that's what we call survey design. So that's what they did. So from like, I'm not 100% sure, like they got probably a lot of wells and some seismic data. So they actually set up this geological model having five layers, got a C. So here in the paper, they didn't talk about what is the kind of the thickness of the sea. It seems like quite a bit. They got big trough. There you could have like 3,000 meter, but you could also have some shallower part about 500 meters. So I think here is quite varied. And I think to set that up when you're actually making a model is quite important. It's like similar to topography on land case, because like if you are in the shallow water, your air wave could make a pretty big impact. So anyway, so that's what we got, and then I think it's quite similar values that they got from the paper. So they set reasonable values for that. So here they didn't include the halite, but they include the LAS, which is a resistive layer, and sediment layer, and the post and pre is about 0.5 and 1.5, and the basement is 400. Okay. And then each sediment layer has some isotropy values, higher than isotropy values. Okay. So I think here the target for the EM and MT survey is LAS and the basement. Yes, you're going to distinguish them from other sediment layers. And so they use some EM code, 3D EM codes to generate synthetic data, and then invert it in 2D. So it's showing one 2D line. And so the top part is C plus the sediment layer, which is blue is conductive and red is resistive air. So you actually quite recovered well this LAS part. And then below the LAS, you got the conductive sediment, which is PO, post POES, post ES. And then also the basement. So MT actually does a pretty good job kind of figuring out the general structures. Okay. And how about the CSEM? The CSEM did a really good job on actually imaging the LAS unit, which we're interested in, but not the bottom part. Okay. Why is that? Why MT sees it, but CSEM doesn't see it? What could be the reason? So for CSEM survey, MT survey, what's the main difference?
The source.
Source. Okay. CSEM survey uses the source, and then MT is like kind of passive, right?
Yes.
For MT, frequency is important, right? So I think here they probably use low enough frequency to see deeper. Okay. And then for CSEM, what could have been make this better?
Lower frequency.
Okay, that could help. How about the other?
The power.
Power.
It's limited.
Go back. Let's think about it like a DC survey. Like what was the very important part to see deeper?
To improve the distance.
Yeah, separation. So if they used the larger separation, they could have been seeing deeper. But I think compared to MT, in this case, that's limited. And that's the usual case. So with the MT, they want to see deeper like a basement. CSEM, they want to see a little bit shallower part, but higher resolution. So I think that's sort of what they expected, and that's what they got. And I think from these two images, okay, I think I have a pretty good chance to image LAS and basement by using both CSEM and MT. So MT can like help to see basement here. And that was the real survey. That's the Red Sea area. So you remember, like that's their trough here, where they got deeper part of the sea, and other parts are a bit shallower. And they got 3 blocks, and in general, they actually used the 350 receivers. Do you remember? This I don't have a picture. It's like an ocean bottom sensor. If I'm making an analogy, seismic. So they used the 650 ocean bottom sensor. I'm not sure how big it is if that was the case for the seismic, but I think in terms of EM, that was a huge survey. That was the largest survey they had done. And they got, like I said, they got greed of the receivers along like a 30 kilometer by 100 kilometer region. That was the survey. And the inline offset was 3 kilometers, so each line has a 30 kilometer offset. But in inline, they got much higher sampling rate. Cross-line offset is 12 kilometers. They measured the EX, EY, BX, BY. So use the horizontal component, measure the horizontal component. And the transmission frequency of this CSEM was 0.2, but you can get the harmonic. So here, it's a little bit different from that one case, like what they're injecting is not exact, but they're basically injecting some sort of like a square, having 0.2 hertz, so 5-second period. Then you can get the harmonics, right? If you Fourier transform it. So that's what they. Okay. So you can get like a kind of 4 to 5 frequency here. They're putting one waveform. So they were focusing on 2 areas. They did the survey on 2 areas. We're going to focus on area 1. Okay. So processing and interpretation. So here we're going to first just focus on like what they call data driven. Here that means we're not using that much a priori information. Here we're sort of like thinking about we're blind. Although you may need to put some information, but then once you get the data-driven inversion, now you're going to put some sort of constraint of seismic from the information that you can get from seismic or well logging. So that's sort of 2 parts. So we're going to start from the data-driven first. Okay. Here's the data. So this is data. It's like a spectrogram. That might be the right word. This one is actually obtained from just one, let's say this is the ocean bottom. Then you have one receiver station here, measuring EX and H, Y, and then here you got the coil, measuring HX and HY. So that's, I think that's one component measured here, the receiver. And what's happening here, I think you got a ship, right? On the seawater, on the surface, and you have the source, and they are moving, right, in time, right? And then they're transmitting the signals. So that's and here you're measuring just the electrical field at the ocean bottom. That's what this diagram like. And then I think you're getting some time series, and then you transform that into frequency. That's what it looks like. So you can actually tell where they actually when they were doing the CSEM survey, when they were doing it. Yeah. From the image, can you tell which time they did the CSEM survey?
Repeat, please, the question.
So this is a diagram.
Okay.
Sorry, it's probably a bit complicated. So if you look at here, you got some peaks, right?
Yeah.
So I think that's so this is at 0.2 hertz. Remember, the transmitting frequency was 0.2 hertz.
Okay.
So you're going to get some harmonics, right?
Yeah.
If you Fourier transform it and then plot it in this direction, right? So that's when they were actually doing the CSEM survey. And then other parts, so they're like continuously measuring. Right? So they're getting both CSEM data and MT data together. Right?
So they wait until the ambient noise does not appear in this frequency that the CSM works, and then they fire the CSM?
I think they probably kind of analyze that, but I think they'll just keep measuring it. And then here you can kind of this part can be used for CSM data, but other frequency, like lower frequency, can be used for MT by processing. Does that make sense? So basically, you're using the same receiver to get the CSM and MT data. For MT data, well, you need lots of time series, right? Longer time series, you can get better a low frequency data. So yeah, you've got more days, and your quality of data could.
I was thinking like if you look at between day 12 and day 20, you have a lot of amplitude.
Yeah.
The noise amplitude, the natural amplitudes in the same range of frequency as the CSM. So maybe if you measure the CSM in these later days.
Yeah, I think they might kind of like try to evade that. I'm not 100% sure of the real survey details, but I think from the image we can actually imagine that could be the situation.
So in this chart, the red color means higher amplitude?
Yeah, higher amplitude. So I think it's 10 to the 6, 10 to the minus 6 to 10 to the minus 10, I guess. Okay. So that's the data looks like, and the frequency band is 0.2 millihertz to 2 hertz. Right. So there are some diurnal variation, and there are probably some solar activities which changes your MT signals here. And here's our data. So I think, can you see that this black dots? So those are where your receiver are on the C bottom. And then you can transfer your MT data to an apparent resistivity. Remember that? And then here was a 3D survey. So you're going to get both TE and TM mode. If you actually compute the determinant of your impedance matrix, it's kind of what they call MT invariant. So it's the kind of doesn't matter of the direction. So it's rotational invariant. And you can convert that into apparent resistivity. And what's important thing here, you can see some sort of a high resistivity anomaly and also some conductive anomaly. So data are kind of changing and smooth, right? So like if you're looking at that image, if there's something really changing a lot, you might be, well, it could be noise, right? But like if they're changing quite smoothly, I think I might, that's probably some signal that I'm getting. Right? So like so far good. And so you have lots of other data set, right? Like, so got some logging, seismic. So they actually built the geological model. And then if you slice it, that looks like that. So this part is where you got halite, the resistive halite. And that's where you got some plastics in the LES. And if you're looking at those two images, they're quite matching, right? So resistive area matches to halite, and the conductive area matches to a plastic for LES. So by looking at that image, like the data they've got seems like a high quality data. Okay. And they took that data, now they invert it using 3D MT algorithm, and that's the recovered resistivity model that they have. So looking at it, so I think that was a pretty big inversion. So the cell size was about 200 meter by 200 meter, but you're covering like 30 kilometer by 100 kilometers. So the total number of cells is about 9 million, which is pretty big. So I think you need a large computer to run actually this inversion. Petrobras may have a pretty big cluster, I guess. You guys can run. Is that right, Sergio? Yeah. Oh, wow. Yeah. So what was the biggest EM inversion that you have done?
I can't tell you now what that is.
It's about like this size, like that much big.
Bigger.
Okay, wow, cool. And the number of receiver they used 198. And
we had one with 30 million of cells, but it's not the biggest one.
Oh, that's cool. Anyway, so here they used the self-log model. So they kind of generated a self-log model, which is actually like picking a LES boundary and then just setting below that as a resistive model. And then they used that initial model, and then that's what they got from their version. And it looks quite good, right? Like the first thing you can see, we got some resistive basement and also resistive LES. So first order, we got actually a pretty good inversion reserve from MT data. And then you didn't use that much A-prime information here. That's actually good. Right, so I think that's what they say here. So I think it's LES plus halite, and that's the base. Okay. Now we're moving to CSCM kind of data. So we're gonna do the similar thing. We're gonna get the we have a CSC data, take that, invert, get a recovered model. So that's what we're going to do. And remember, CSM data, we have two types of sort of geometry, inline and broadside here. So to actually get the broadside, you need to grid the survey. Right? So here they got kind of like a 2D grid of the survey, so you can get the broadside. And right. So in inline, assuming the 1D structure, what you can get is EX, right? You're getting the EX component, or EZ component, or HY component. If you're measuring other components than this, that means you're having some other structures, like 3D structures. And broadside, you can only get EX, HY, HZ. Okay. And that's the data they have got. So this one is inline data from 0.2 to 2 Hertz, and they are changing. So 0.2 is this guy, 0.4 green, and as you go higher frequency, the amplitude decreases. Does that make sense?
Yeah.
Why is that? Walter? Why is that? Pardon me?
Sorry, what it was?
As frequency increases, your amplitude decreases. Why is that?
Because the higher frequency, I'm more absorbed by the Earth.
Okay, attenuation, and then what was the terminology you used to explain like a higher attenuation? Skin depth. So we're getting higher skin depth, so it makes sense, right? And then up to 25 kilometer, your quality of data is fairly good. So I think, can you see this here, like kind of changing a lot, this part, as you go higher frequency? And that's where, oh, okay, there might be my noise level. So I think you can go up, your noise level is up to 10 to the minus 16. And if you look at the perpendicular line, or broadside, actually here, you're only expecting EX, right? If you got just a 1D layer. But you're getting EX, EY, and other components. That means you may have some 3D structures. That's what this plot is showing, and that actually is pretty high quality data. So by looking at the data, you can actually do some sort of QC, and also expect, oh, there might be some 3D structures that we're seeing here. And Doug was mentioning this a little bit when in MT, or like when he was talking about Csa Mt. If you go far, if your offset is far enough, now you can use the MT assumption. So you can basically use the kind of this formula for apparent resistivity, transfer your data before to an apparent resistivity and the phase. And as you go like a longer offset, it kind of asymptotes a certain value and a 45-degree angle. So I think it's a good way to check, or a good way to QC your data, because that's physics, what physics tells, and then your data looks like that, then it looks good. And here's CSCM and MT data together. So this is MT data at 0.1 Hertz. And if you pick a kind of similar frequency for CSCM data that's at 0.4 Hertz electrical field, and they're looks quite similar, right? There are probably some difference, but overall, like they're kind of pretty high. They have a pretty high correlation, and they are matching with the like kind of their geological interpretation from seismic as well. Okay, now take that data, invert that, and you can get the resistivity model. Looks like that. And here they tried two different initial models. I think we're gonna talk about the inversion, but our inversion is non-unique, and there could be a whole bunch of different models that can explain your data. That means you need to try like a multiple inversion, not single inversion, right? So what they did is say, okay, I'm gonna just change my initial model. The first one, I'm gonna take the same initial model that I have used for NT, inversion. And the other one, well, I've already got the 3D MT resistivity model, so I'm going to use that and then for my CSM inversion. So that's what they did, and that's what they got from CSM inversion. And I think the result doesn't look very different. So overall, you recovered this LAS part pretty well, and that matches with your well logging. I think that's good. But it's hard to see the basement from the CSCM. I think we need MT actually to see the resistive basement, and that's what it can do. I think here, do you remember what they did here? Because there were anisotropy, right? So the sea sediment has some anisotropy, like different resistivity for vertical direction and horizontal direction. Here they didn't take account. Not 100% sure. I think it's probably easier to start with some like a homogeneous case, then move on. But so in an initial state, they didn't use that. So I think it was hard to converge. So that it did not converge. You got the model, but it did not converge to your target misfit. So there probably you need to take account. Okay. So we're going to do that in the model-driven approach. So that was okay result, but there was a problem to fit the data. Okay. Now we're moving to a model-driven. So from the data-driven inversions, we got a good model for 3D MT resistivity and CSCM resistivity, although there were a couple of challenges. Now, well, but we have a lot of like other information. At least we got seismic sections from migration, and also a lot of well logging data. So we're going to use that to get the better inversion results. So we're kind of now narrowing down to have high quality resistivity inversion results. Okay, so I think that was now we're starting from the MT again. This was the data-driven inversion result. So I'm showing the section view of the 3D MT inversion result. We're at the LAS and basement. Right? The second, now here, what we're going to do, we're going to remember here, we got the LAS quite dry, and the MT, what's the main thing that we're interested in? But we want to see deeper. So I want to image the basement better. So what we can do, okay, I'm going to fix based upon the interpretation and well logging data. I can actually pick some horizons for LAS and then assign the reasonable resistivity value, and I'm going to fix that. Okay. So this part is not included in the inversion. So I'm just inverting for this bottom part. Okay, to get kind of higher resolution for this basement. Okay, so that's what they did, and that's what they got. And the second trial, okay, that's what I've got. So what they're doing, they're just trying to get in closer to, I'm not sure what's the true solution, but what they kind of better result. So that's where I am now. I'm going to use that as a starting model, and then invert the full data set again. Now I'm sort of like letting all of my cells to be inverted. Okay. Does that make sense? It's kind of complicated. So start from MT, fix this part, invert, you got it. Okay. Now you use that as your starting model, and then invert for everywhere. Okay, that's what they got. So you can see some structures they're getting on this LAS. Okay. So because that's what they want to see. In the so in the first part, as a first order, I want to see the basement better. Okay, now I got it, but I still want to narrow down on this LAS part with where is my plastics and where is my halite. Okay. So that's what they're trying to do. So you can see some differences here, but maybe not great resolution. Okay. So that's empty. Now we're moving to CSCM inversion. So here, well, you got pretty good model from the MT inversion. So we're going to use that MT inversion result as an initial model. And plus, you're going to use some boundaries that you picked from both seismic and the well logging. So this is a kind of, if I pick AA prime here, and that's the initial model that they use. Okay. So you put I think they kind of like, this is what they got from here. So I think that's where your halide, and that's the full LES sequence. And that's your initial model, and you invert that. That's the resistivity section or plan view map that you got from the CSM inversion. And here they actually take account the anisotropy and they could fit the data. So that's actually good. And this is the vertical section at AA prime. So compared to here, right, you're getting more structures, right? So this is where you got halide, and those are defined like a kind of clastics that you're getting, what they call mini basins. So you're seeing those. Now you're distinguishing your mobilized halide and the clastics, right? And then clastics where you could potentially have a reservoir either below or probably inside the LES, I guess. So that's actually great, right? So that's what they want. So you got the basement from the MT, and now you're really narrowing down in the LES to distinguish clastics and the mobilized halide. And I think that's probably where seismic imaging have challenges, right? If you got this much lateral variation, I guess, then actually getting a good migration result or velocity model might be a challenge. Is that right? Okay. Like, are you guys doing? Is Petrobras has a problem for like salt domes and imaging?
Yeah.
Yes.
Okay, so what's
Talk to this guy.
Oh, all right. Who's the expertise for salt dome imaging?
Generally, you have to use the horizons to invert a good model. And the problem is when we don't have a good base for the allogenous salt. So we try to use the graph data to try to estimate the volume of salt, not only using the.
I see. I see.
But it's difficult.
I see. I see. So you like, and then you're like based upon that you're generating some velocity model and then use that for migration.
Yeah, sometimes we cannot see one flank or one base of the allogenous salt, and we try to use the graph and this kind of data to estimate the volume of salt and pick one base, one allogenous salt base to put across the model.
I see. Yeah. I think so. I think it's a pretty big challenge, I guess, and then having a high resistivity model somehow convert it into velocity and then using that as a migration. I think that's sort of a big picture here.
With the graph data too.
Right. So I think I'm going to show one image of that as well. And so here we're kind of just comparing how the resistivity model and velocity model look like. I think that's the velocity model they have used for their migration. And I think overall it's matching. You see the kind of high resistivity and high velocity structure, potentially mostly halides. And yes, I think you can see those structures, and in this part, I think it's not quite matching. I think they were thinking, oh, we were actually overestimating the velocity. So I think this part potentially could be improved by using resistivity. Right. So I think that's we spent some time to actually get the MT inversion result and CSM inversion result. And we started from the data driven, just using kind of like a blind start, or in the model driven, we actually got a lot of A prime information, inject that, and then we can get the better resistivity model. So this was the actually starting model from MT plus geology. That's what they got from MT and geology. And now by using the CSM inversion result, you're getting a higher resolution in the near part in the LES. So you're getting some sort of like a conductive clastic sequence, clastics, and then distinguishing from the resistive halide. And that's this is called like a model update. If you subtract this from that, or this from that, that's actually the model update, right? That was your starting, and then what is changing? Right? So some portion is getting more resistive, which is red. That probably means higher halide concentration, more salt. And the blue is like more conductive parts, probably less halide concentration. So it could be a kind of meaningful section, right? And I think it's quite like consistent with their migration research, if you look at the boundaries. Right, so I think the synthesis from MT, actually we got the overall like structures, LES, resistive LES, and the basement. And by using CSM, we actually could really narrow it down in the LES layer to this, like and then distinguish the resistive halide and their caustic setting. And by using some A-priori information, actually they really narrowed it down and then got the high quality resistivity inversion measure. So I think especially in 3D, that's very important because there are a whole bunch of, like, it's much easier to fit the data, and then you can get a whole bunch of different models. And what is a good model? So I think here, there could be a lot of different strategies that you want to use, but they actually have shown a way that you can really narrow it down to get a good result. And the other thing was they actually also did the gravity gradiometry. So it's basically the derivative of your gravitational field. Second derivative of the gravitational field. And that's what they got. So this is the density inversion result, 3D gravity inversion result. And I'm showing you the plan view at quite deep, like where you got the basement. And I think you got this high density. That's where you probably have a basement. And if you compare that with the resistivity section that you've got from MT, I guess, and that's where you have a basement. So I think it's quite matching. And that's where you got halide. And the halide has yeah, and then that's the gravity data on plan view. So you have low, and then where you got halide, gravity low, and gravity high, where you got basement. By inverting this, that's what you got, and that's where you got basement. So I think they didn't really kind of jointly invert this, but they got 3D inversion result and paired with resistivity, and overall, I think they are matching where you got basement. I think you guys, like, this is probably useful information for 3D seismic processing as well. Like density model, use velocity, use for the velocity. I think, yeah, so that was it for this case history. Yeah, I think it could have been better. They kind of not ending here. Okay, now that's what we've got. And how can we use to actually get better velocity model and migrate and iterate back, and then how much difference you can make in your reverse time migration. That could have been quite cool. But I think even what they've got is actually a pretty good result. They are maybe working on it.
The gravity were used only to match the structure, not inverted the gravity base, to see or modeling the gravity base to see in depth. You are only seeing the data, the Google anomaly you map, and matching this to your results.
Okay? So what's your question?
You just are seeing the Google anomaly,
right? Yeah.
And compare it to the results came out of the EM inversion.
Okay.
So it were used only for this purpose to see, compare.
Yeah, I think they were showing that I think what they're getting in terms of the model is actually like you can see some correlation, right? By looking at the data and the model, you can see where the lows and what they got the low density model. I think that's sort of matching. I think it's nice to show both because like the inversion, it's you could get like a whole bunch of different models, and then if you're not really seeing from the connection with the data, it's kind of hard to tell the quality of the inversion reserve. So it's nice to show data and inversion reserve together. I think that's what they want.
Because a really complex area, maybe
could be, yeah. Sometimes just looking at the data, like you have no idea, so that's could be a motivation to invert as well. But I think like kind of showing this like a low, like a very smooth data shows that we got high quality data. Also another point there. Sure, here. Any questions?
So what's your input signal for your MT inversion?
Input signal for the MT inversion.
So you have your model,
Okay.
and so you need to have some kind of source, right? It's natural source.
Yeah, so that remember that thunderstorms and they'll show that movement of charges getting into.
So how do you get those data?
Oh, I think we don't really know that. So that's we don't know actually that information. So that was why they'll show that processing was very important. Right? So you're actually just getting the signals from your receiver, and with some kind of sort of stochastic processing, you can convert that into an impedance values. So I think that was quite important. Right, and that's sort of the beauty. So I think there are a whole bunch of MT sources coming into the Earth, but you don't really know that.
And how do you do your forward modeling?
In the forward modeling, I think to get the kind of that information, we just need two polarization, like a two unique kind of orthogonal polarization, electric field in this way and that way, and set up the boundary condition like this and that. Then you can actually compute the impedance tensor. So Zx, Zxy, then you can convert that into either apparent resistivity or phase. Then that's your data, and you can convert that.
So you were used for all their kind of MT inversion as their kind of.
Yeah, that's a center. Yeah, and that's in frequency domain. So that's what.
The size of the model, of the image model, is the same as the size of the CSEM?
I don't think so. I think that their cell size probably need to be smaller.
But also the boundaries.
Yeah. Well, I think MT you need much bigger boundaries. So I don't think they're using the exact same mesh. Because then like a CSEM will be really expensive because you've got smaller cells and then that much boundary. Okay. Thank you very much.
Okay. Thanks, Aki. So let's break for a coffee. And we do. And looks how we're getting two polarizations. Yeah, and then how I should Great. So yeah, that's very nice.
Yeah, it's complicated. So you're going to do anything wrong?
No, I think I'll well, no, I need to just say something about chipper data, and then we'll go on to the
Inversion. So I think now it's changed. I think that most of
I
things
think
are.
the only thing I need to do is to get the forward modeling and then
Right, so I think now you could do it in the two datum stuff, I think if you want, you could do it. Virgin. So just remember, like if you want to start, just start with that screwing things up. Just set the floor at 0, make sure.
okay,
Okay. Just, yeah, you could just run, well, like a run.
shift enter.
Enter. You can just keep shift enter.
Okay.
So shift enter, I think. Okay, that's the co-op. So that's default. Okay. Can you just like make it a little bit? So where are we? Oops, where are we?
Here's our slides.
Oh. Slides.
Put slides on desktop 1.
I think it's that's the top 1.
Yeah, so the apps on desktop 2.
Two. Oh. Is that fine?
I just want to see the slides on desktop 1.
Okay, the 3-finger. So now, okay.
Okay, so we can actually. Okay, so I first want to build a model.
So now you could do one data.
Yeah, actually, I want to build a model first.
Oh, okay. Make sure you run this first, and then just go. Like, just keep running. No, you can just keep running. Okay. Shift enter. Click first, or just keep enter. Go there. Go down.
Can I do a run cell all and then
Yeah,
just
you could
everything?
So,
So,
and then like make sure that goes to empty circle.
right, well, we'll be, I'll just come here, right? Here's our app.
Right.
So the first thing I want to do is build a model. So we've got. Okay. And so two. Okay, so we're gonna build a model. And then we have then we're gonna go back and say, okay, that's the thing that we're looking for, so we're going to set up a survey, okay, right? And then now we come back here and talk about, so if I just wanted to get, let's suppose I just wanted one datum.
Yeah, you can type 1, go all the way left.
Here's the datum. 100 cells. P minus 0.15 Q. Oh, we got J1. So we're
1 is just, I think it's J1. Okay, J1 is 1. Okay,
right, but I got
one.
J. What is this 19? Like I've got one datum. How does that fit in?
Yeah, like I didn't have a chance to change. It's still like was 1 to 19 and number of n. So
they're all going to be superimposed on one. I'm a bit confused.
so remember that J in the equation.
Yeah.
So like yeah, we're gonna just start from 1 to J1 to Jn and then linearly space that in terms of n.
Can we just get rid of J?
Yeah.
Okay, so I've got one datum.
Yeah.
Do I need to worry about these at all?
No.
Okay, so I just got one datum.
Okay.
And
yeah, okay, let's not change those.
Yeah. So I got
one single
value. And that's what my kernel looks like if I wanted to make it oscillate. Or something like that, right? Can I?
No.
Okay. Well, you can do it, but it'll do that and see what happens. So I can just click on.
Oh, I see. It just goes back to 1. Okay.
But you can increase your J1 if you wanted to oscillate.
Yeah, if you wanted to.
Oh, like I could do.
Okay.
Okay.
And then click. Yeah, there you go.
Okay, all right. Okay, that's fine. And then, so let's go back here, go back to 1. Do I have to do shift enter or just?
Just enter.
Okay.
Oh, just see what you did there, Doug? You have to be careful.
Yeah.
You can make sure you always
Oh.
click outside whenever you're done. Okay? Yeah, so 1 and then just click outside of it.
And then,
Because otherwise, if you accidentally scroll, it scrolls the numbers.
oh, I
If you're
see.
still inside of there.
Okay.
Put down.
Okay, so now we've got,
So here, like a command and data.
right.
So by default is that shows the error bars, but you could kind of just click. Then just apply.
Okay. And then we could do. Okay. So I could go back then and change M1 center. Put it up over here. And make a negative value.
I think you passed the 1, so I think I should have bounded it by 1. I need to go. You may not want to go over 1.
Right. Yeah, so now that number is negative. And it's still negative. Okay, that's good. This-
If you want, you can add noise.
Okay, so we're going to add noise. So let's go back and
Increase and
increase in to
you can type. There's a bounds.
okay. So now I got
So can you click and make sure you hit enter? Yeah, click enter. I think that's
it's a bit different. What did we do here?
Can you just shift enter, like a restart this one? Shift enter.
What happened?
No, I think probably like that was a bit different Q you used. You increased Q a lot.
Oh, okay.
So
Okay, so now
I think you just need to click.
add noise.
Yeah.
So we're going to add noise.
Then it will change.
Wait a minute. Okay, so we're still in it. So we add noise. Okay, good.
So it will just update.
Okay. So now I got these data. Now I want to. This is good. Okay, we got 30 iterations. Okay, so now I have to change the.
No, I think you just need to run. Like I just rerun. Okay. And
So looks like
now
that.
I
But
think you need to just click run because it. Okay. And you go all the way down to the maximum iteration. It shows you when you got to okay. So that's probably what you want. That's not what you want, I guess, right? You want to show really like a screwing reserve.
yeah.
So for that, just set the floor 0
Set the floor 0.
and run.
Enter.
I think it's good. Once that's done, okay, just click run. Now it's actually start from whatever iteration, and then you can just move around. Zoom's not screwing that much for fine. It does. That seems like okay. I think as long as you make sure set the floor 0,
Yeah.
it'll just go up. So. And here, if you want to comment up the technical curves, then you can take them. Oh, that's a bit abrupt. I think for that, you probably rather set alpha as to now back, like I think that was the abrupt setup. Now you may want to set the alpha as back to 1.
Okay, so let's. I think chances of me screwing things up, especially in my state of mind, are pretty high. So let me get part way through. Let's just start it back from default. How do we do that?
Ah, cara, cara, deixa eu ver. A gente não trabalha lá, né? Eu não trabalhei lá, mas.
You can just talk about how it looks like and start from the bottom. It does the inversion. You can actually basically show everything and start from model.
Yeah. Okay, so I think what's probably going to happen here is you can just be on quick standby because you're going to be up here pretty soon to make sure I'm totally toast. Yeah.
Voice parameters too.
Yeah, maybe that'll
Because
actually
there's
work.
like little subtle points about getting it to run, so why don't you just talk and say,
Yeah.
set it to this and this.
Okay, I think maybe that'll probably be the best, otherwise it's just too, a little button here, a little button there, first thing you know, you kind of lost the connection with the audio.
Yeah, well, and you've also lost connection.
Oh, I don't have to worry about that, I do not have a train of thought, there's no train. There's an occasional car that's moving along the track without an engine. Without an engine. And then that's about it. It's like, oh, okay.
That's fine. Some music could drive.
Okay, yeah, that,
We'll
I
get his
think,
driver's license here in Houston.
oh,
Very
okay.
excited. Very excited.
Okay. But it just keeps changing.
And it's a complicated after run.
Well, there's just a lot of subtle things.
Oh, the link is on
Okay. Well, all is.
That's fine. So we
the train is not a train, but there's something on the track that's moving barely.
That's all right. Round everybody up.
Yeah, I just gonna go to the one.
So it's like a web page.
Pra cerveja, pessoal, eles fazem.
Cara, mas se juntar a cerveja dos pais dos aniversariantes, a gente vai beber bem. O que bolou todos esses churrascos aí.
Hoje à noite, minha conta, que eu não na festa lá. Você já tá incluído já, não? Olha aí. Eu ouvi. Os caras não sei aí, viu?
So then they would be later.
Faltando cerveja ou outra. Almoço, vai falar coisa.
Yeah, so the target.
Yeah, so basically, expanding the target materials.
Então, você de cada vez, tipo, assim, essa aplicação, 15 minutos,
It's a complicated geology.
mas está bem vazio. Dá pra até fazer tipo de atividade. Então, almoço? Já ia assistindo a geral, né? Pega, né?
Quando menos.
Ah, mas acho que eu fiz esquerda, né?
Aqui, Sérgio, tem uma suposição aqui, mas é de área de vídeo, tá? Não sei se são vazamentos são de mais ou menos 5 mil metros, o reservatório é 4 mil metros, a água
I'd like to make some comments about a related natural source technique that has become very important for the mining industry. And it's actually a very good way of doing near surface structural, getting near surface structural information. And of course, anything near surface might actually play a role for the oil companies. So I just want to, I don't want to spend a lot of time on here. We could come back if there's some interest, but we want to move on to the inverse problem. So imagine, first of all, that we got this MT signal coming down. So we thought, well, we can just think about a vertically propagating wave. That wave might have an electric field in the x direction and a magnetic field in the y direction, and it's propagating vertically down this way. So it's just a plane wave that's moving down. If you have, so let's draw a cross section here. So this is a cross section in the Earth. So this is Z, and this is X. If coming down here, you've got a resistive or a conductive block or something, then you've got an electric field that's going this way. And we know what's going to happen to that, right? So the electric field is coming in this way, there's currents that's going in this way, so there's going to be charges that are built up, and there's going to be currents that are generated. So these currents that are going to be built up in here are going to give rise to a magnetic field that can be measured. So if we thought about a current that's kind of channeled into this guy here, so now we've got a current in here, and that's going to, by the right-hand rule, give us, a magnetic field in this y direction, and also in the vertical direction. Then we could think about measuring that and getting some information. So there's something called the tipper. That is it's a geophysical datum that's just related to magnetic fields. So we've got currents that are going in, currents give rise to magnetic fields, and the idea of this experiment, which is sometimes called ZTEM, which is Z-axis tipper electromagnetics, is given by the following. If we have natural sources, they generate currents inside the Earth, so that gives rise to a local magnetic field. If we take the ratio of, let's say, the vertical component of the magnetic field at some particular location here, and compare that with the magnetic field at some remote station, then that's actually a datum. What it's telling you is that it's kind of like a relationship. It's another one of those sort of transfer functions. Like, okay, how does the vertical component of the magnetic field here compare to the horizontal components over at this base station? And then you can just fly this guy around, back and forth. You just measure the vertical component of the magnetic field, and you get now a relationship that the vertical magnetic field at this location here is dependent upon the x component at this location back here and the y component at this location. So this is the Tipper equation, if you like. And there's only two components that are needed. When we did the impedance function relating E and H, there was 4 components in that impedance function. Here, for the magnetic transfer function, we just need these 2 guys. The experiment then is to basically do exactly this. You set up this remote station, you fly this loop here, which measures the vertical component of the magnetic field, and you just fly that thing back and forth. You get these Tipper coefficients, and then they become your data. And you can take those data, and you'll see your data, which now, because we're in the frequency domain, we'll have a real and imaginary part, just as we talked about before. And you could go ahead. Data sets will look like this at each frequency. You'll have sort of real and imaginary parts. You get images that look like that. That's your data. And you could go ahead and you can invert those to recover 3-dimensional resistivity models. So that's another whole set of data. It's, as I said, a very good geologic mapper to try to find lateral changes in the Earth's surface, and you can actually get down to perhaps a kilometer at depth, and it's been very useful for the mining industry. So we got a case history about that. That's really all I wanted to say. I just wanted to bring it to your attention that, okay, there is another datum that you can use that really makes use of natural sources, and it is potentially of value to you. Okay. So now we're really changing gears at this point. We want to start talking about the inverse problem. So the inverse problem is something that is completely ubiquitous. Doesn't matter which field of geophysics you're in. In fact, it doesn't matter which field of science that you're in. One always has observations, and you want to somehow use those observations to tell you something about, the system that was used to generate those particular data. One of the things that we discovered as we were going around last year for the disk, there's a lot of people out there that are using inversion codes, and you talk to people who are using the code, and it sounds like they're really knowledgeable. Like they talk about data misfit, they talk about model objective functions, they talk about Tikhonov curves, and all this stuff, and you start to think, these they really know what they're talking about, and then you dig down a little bit, and you realize like they don't really understand some of the fundamentals, and the fundamentals are really important. So kind of understand the relationship between your model and your data, understanding the non-uniqueness that's in your problem, and how to contend with that. These are actually critical issues. So we want to start to address those. We're going to show some simple linear problems, and we've got an app which has been developed that allows you to kind of play around with this and get a lot of insight. And then we'll follow that up later this afternoon with some nonlinear, or some tutorials for the nonlinear problem, particularly the magnetotelluric. So now that we've kind of seen that, we can kind of tie things together by looking at one of the survey techniques that we've just been talking about with the So we've seen examples, we've seen lots of examples of inversion. We've got some data, and then the question is, what is the Earth model that gave rise to this? What's that distribution of physical properties that actually gave rise to these data when that was the particular survey? So I just want to establish a little jargon at this point, just to make sure that the words that we're using are completely understood. So first of all, there's something here which we will call AM. That's our model. This is, in most cases, a physical property. Maybe that's electrical conductivity. It could be in 1, 2, or 3 dimensions. It could be any other physical property. And then we've got some way of forward simulating the data for our particular survey, whatever physics we've got, and we're going to denote that by F of M, and then D are the data. So the forward mapping connects the model that we're at and the data. There's a couple of kinds of mappings in general. They could be linear, could have linear mappings, so this could be a linear forward problem, or it could be a nonlinear problem. The difference is that in a linear problem, if we take two models, like M1 and M2, and added them together, that we could decompose that into like some coefficient for the first model and a coefficient for the second. Another linearity holds. In a nonlinear problem, that equality just does not hold. So in one case, the forward simulation from model 1 and the forward simulation from model 2 is the same as the forward simulation of model 1 plus model 2. For a linear problem, we can write it as Fredholm equations of first kind, which looks like this. So we've got data, which is some integral over a volume, could be 1D, 2D, or 3D, of a kernel function, which we'll call G, and your model quantity M. So this is the relationship between the jth data and the model, and the kind of viewing, or the way that you're kind of viewing this is through this kernel function here, Gj. So one could have a model then that looks like this. It could be a boxcar and some kind of a Gaussian, and the app that will take you through will have that. And then this kernel function like that. So the datum that you would get from this is the inner product of this quantity on here. So that means that we could overlay this kernel on top of here, do that multiplication, integrate it up, and we get a number. And in this case, that number would be positive and be value of 4.89. The linear problem can be like just this one. Everything is here just in one dimension. Or it could be in higher dimensions. So there's, let's suppose you have a cross-well tomography problem. We saw some of those. So we've got a source and receiver. The wave might go from the source to the receiver. You could have straight ray tomography that would mean that it propagates right along this line, or you could have some other relationship. So we can relate the travel time, if we like, to the integral of the slowness along whatever ray path that we've got. So that would also then be a linear problem. So this would be a two-dimensional problem. Three-dimensional problem, again, we've seen, could be the magnetic problem. So here's a magnetic problem. Kappa is the 3D susceptibility, and here's your kernel function that you've got that relates the magnetic field, which is now a vector, to what this susceptibility is. So 1D, 2D, 3D, these are all linear problems. They can all be portrayed as an integral of the thing that you're looking for, whether it's slowness or susceptibility, with a pre-multiplying kernel function. So solving the forward problem, we've got something that looks like this. And as I said, this volume could be 1D, 2D, or 3D. So if it's 1D, we're going to discretize it into, say, cells that are just layers. In 2D, then these are cylinders that go into and out of the board. In 3D, these are just cubes. But it doesn't really matter what these are. We can always discretize this in such a way that we write that the data, which could be now a vector, is some matrix G times M. So M is going to be a number of them is however many cells you have, whether it's 1D, 2D, or 3D. And we'll use capital M as a descriptor for how many parameters, how many cells that we actually have. So the nonlinear operator, that's mostly what we've been dealing with in this course. We can still write it notationally as f of m is equal to d. So f is Maxwell's operator. So it could be the DC resistivity operator, in which case the equation looks something like this. It's div sigma grad phi. Or it could be something that's in the time domain or the frequency domain. So here's a generic expression for Maxwell's equations. And this also could be in 1D or 2D or 3D. So here we got a couple of nonlinear problems that we've been talking about during during this week as far as applying them. So for the nonlinear problems, whichever way we are, in order to solve them, we have to take Maxwell's equations, we have to discretize that onto some kind of a mesh. That mesh actually could be a tensor mesh, a rectangular mesh, or it could be a cylindrical mesh as you have in some of the apps. But we do need to discretize it onto a mesh. And then we've got to solve a system of equations, either to find, in this case, the potential, or in this case for EM, to try to find E, the electric field. You can also formulate it to try to find H, all kinds of things possible. And then once you've solved that equation for, let's say, the electric field, then your data could be some function of that electric field. It could be the kernel of that electric field, which would give you a magnetic field. It could be an amplitude of that electric field. It could be a phase if you're in frequency. So that's the situation. So you've got a differential equation, discretize that onto a mesh, you solve that system, and then your data are some function of those parameters that you just solved for on the forward problem. So there's a lot of details, and these can be very computationally intensive problems. And you've got large numbers of cells. We've seen examples this morning where you have a few million cells. Sergio was talking about an example where they had 30-odd million cells. That's a really big problem. So there's all kinds of details about how big the mesh is, because you have to worry about boundary conditions, the expansion size of cells, where you make things small, where you make things large, lots of details. We're not going to go into those. We're just going to kind of look to see how the inverse problem works. Later this afternoon, Lindsay will show you for the magnetotelluric example, what the effect of some of these things are. If you make cells too big, you don't have enough padding cells, or whatever. So there's an inversion app that we got. I'm going to just kind of go through a couple of slides first, sort of set the tone, and then we'll actually go to the app. And this will kind of set the scene. So the first thing that we're going to do is to generate a model plan. So this is the thing that we're actually going to, to try to find. The app will have the flexibility for you to make quite a variety of models. They're a combination of boxcars and Gaussians. So the boxcar could be located anywhere in this box from 0 to 1. It could have an arbitrary amplitude, positive or negative, and the Gaussian can have whatever width you like, can be centered at some place, and also have an amplitude. So, just two shapes, a boxcar and a Gaussian, but because of the flexibility, you can actually make quite a few different shapes. So that's the model. So that's the thing that we're really trying to find. And then the question is, well, what are you going to do for survey? So let's suppose that we make a model, maybe something like this, right? So this is 0, this is 1, and we want to try to find that. We're going to try to set up an experiment that can find this. And we're going to recognize that we could have we're going to work with this kind of a system, so or linear system. So this is what we're going to try to find. And so clearly the important component is like, what are these kernel functions? So they're the physics. The physics and the geometry of the problem are all kind of connected in with this, and you're free to choose whatever you want. We've made a specific choice, and it's based upon something that I was hoping would make kind of intuitive sense to you. And it's in the following way, where I'm going to plot Z down. But remember, for an EM experiment, so let's suppose we've got some kind of aircraft that's towing a loop over here, frequency domain experiment. And then we talked about the electromagnetic waves kind of going into the Earth, and they kind of propagate, so they're a wave, right? But they also attenuate with something like that, right? If we change the frequency of this, then we still get that same kind of decaying harmonic oscillation, but at a higher frequency, it might be just something then that looks like this. So what we've done to try to kind of emulate that, although that we now change from a Z to an X, is introduce kernel functions that look like this. So we've got, first of all, a cosine function. So here's your sinusoidal functions, and we've got Q, which is kind of related to what the wave number is here, and then another index J, which will allow us to have different sort of oscillation frequencies for each cosine. And then we also have a pre-multiplying exponential here, which gives us we can use that to control the decay. So the P is going to be negative. So the larger the value of P, or as we increase J here, the larger that coefficient is, the faster this is going to decay. So that's kind of a nice understanding about what the kernel functions will be, and we'll just kind of use that to explore to see what we get out. So we got these decaying kernel functions, and then the next thing is the data. So we had that. Oh, I just erased it. DJ is GJ X. So if I have now a kernel function, okay, that let's say it doesn't decay, I plot the kernel function on here, and maybe the kernel function stays constant at 1, so it's just then clearly this is going to reduce down to just 1 times m of x. So I'm just going to be looking, my first datum 1 is just going to be the integral of this model, and so in this case it would be just some positive number, right? If I change this kernel function, and if I make it, let's suppose something that decays really sort of quickly, suppose that it kind of goes down like this, then really I'm not being affected by this region here at all. I'm really only getting some information about this. One of the concepts that's actually really important, and it just kind of depends how you sort of click in with this. You can often think about this kernel function as that, like, those are your sort of eyeglasses for looking at the thing that you're really interested in. So your datum is really kind of some kind of an average of this model, with the sort of averaging function or the viewing function is really that kernel. So that's coming from the physics and the geometry of the problem, but the heart of what you know about this is really contained in this guy here. So that's starting to give us the 3 quantities. Let's see what they are. Yeah, so let's actually get down to that point with the app. So here's the inversion app. I'll just talk you through a little bit of what you're going to see when you open it up. But there's a little bit of a discourse here about what the problem is, and you can see that we've got it's being set up as a linear problem, so that we've got here's our data, here's our kernel functions, and we can discretize that. Just talk about the discretization. So if I wanted to, let's suppose I had a kernel function that was just a constant. So let's suppose I had a kernel function that was just a constant value like this, and I wanted to compute this integral. And clearly one way I could do it is just divide this into a whole bunch of elements. I'll discretize this. Each one of these is some, delta x, and so that means that my d1, okay, is just the sum of m. So now we're going to say that the value of the model in each of these intervals is just the value of a function. So it's basically some mi delta xi, and delta xi is a constant. Then this is just the sum of mi. If the kernel function is more complicated in this, then we could just write this guy here as the sum I equal 1 to n, of g j of xi, whatever that value is, times mi delta x. So that's the way that we could basically discretize this problem. and get a numerical value. We can write then our equation D1, okay, in this term here, it is G1 of X1, G1 X2, G1 Xm, this thing here, okay, times M1, M2, and M. Right, so we could take a vector product of this. So here's our model quantity that we're looking. So it's an array of numbers of like M, and here's the kernel functions evaluated on those same cells. So that would give us our first datum, and then of course we can have many data. So D2 would then extend this, so it'd be the second kernel function. Now like this, and eventually we could write that D is equal to Gm. So D, is a vector. It's got n values. G is a matrix. Sometimes it's called sensitivity matrix. Is got n rows by m columns, and m is our vector that we're looking for, and it's a length m long. Okay, so now we've written our equation as in this manner, and we could go ahead and work with it. So let's just go through this just for a second. So just to show you how this works, let's just first of all think about putting a boxcar in. So I'm going to get rid of the sinusoid or the Gaussian. So here's our boxcar. So we can change its center. We could make it go. Oh, it's over 1. Now, where do you go? Here, you can see better than I can. So we can shift the boxcar. We can shift the boxcar to the left or to the right, and we can change its altitude. We can make it negative.
Yes, sorry. Negative.
Yeah, so we can make it negative. So we got a lot of flexibility to do that, and then we could add a if we want, we could add this Gaussian. So the boxcar is listed with M1, so it's got amplitude and center, and the Gaussian is M2, and we can put that any place.
Right. So I'm gonna just.
And then M2, there we go. So perfect. That actually gives you quite a bit to play with. Okay, so now let's just make a couple of kernel functions. So let's suppose that we just have one. Okay. So let's put one kernel function in. Suppose it's just decaying, and it kind of looks like that. Then now we're going to take this kernel function and we'll plot that with the model. The kernel function. Okay, so here's the thing that we're looking for, and here's our first kernel. It's positive up here. It stays positive all the time. And what we're going to do now is to do the inner product. That means multiplying this guy with this, and then doing that integral. So if we go ahead and we do that, and then we look at the datum. Oh, so first of all, just a second. Hold on. Okay, so what do you think that that number might be at this point? It's actually not so true. Let's make M2 the amplitude really small. Okay, so we got that. What do you think the inner product? What's going to be the value of the datum for this example? First of all, I said, what about the sign? Positive or negative? It's going to be negative, right? So the model is negative, and we're multiplying it by something that's got a positive value here. So yeah, so we might expect to have something like 0.08 times whatever proportion this is. So 0.004. Okay, whatever. Extract. So we're negative value here, and that's our data. Okay, now we can do that for a whole host of kernels. Let's go back and do maybe 20 kernels. So now we see the kernels look like that. So some decay really slowly, some are decaying more rapidly, and so this is the kernel functions. I'll talk about the singular values a little bit later. At this point, we'll just sort of leave these as the kernel functions, and then now we're going to go back to that and look at what the data are going to be for this guy here. So add noise, and this is now what the data are. So data, we'll always add noise to the data, and as we talked about earlier, like a percentage plus a floor is a pretty reasonable thing to do. You don't want to generally just assign a percentage to data, because when you're doing the inverse problem, you're trying to estimate what the uncertainty is. If your data happens to be 0 and you're assigning percentage, then you're going to be trying to fit it unduly accurately. Here we've assigned data that's sort of 5% plus a floor, and so these are the error bars on the data. So now what we'd like to do, so we got 20 data. That's the model that we're trying to find, low velocity model. And now we want to see what we can do. There's a few things that are generally done. Generally what people do is try to say, okay, well, let me find a model that fits the data. Fair enough. That's something. But let's just be concerned only with that at this point, just finding a model that fits the data, and let's see what happens. So we're first of all just going to invert these data. We're going to come back and look at some of these processes. We're going to invert those data and see if we can find a model that fits those data. Okay, so here we have, what we're looking at here is first of all, this is the thing that we're trying to find, this little negative region in here. And initially, our model, we're going to start off with just a 0 value, a 0 estimate. And so the whole procedure is going to be iterative. So we're going to start.
It's a first guess.
It's our first guess. So we start off with our first guess, and like, okay, I don't know anything, right? Overall, I think it's supposed to be 0, but we'll see if we can find some kind of a perturbation. So we started off iteratively, and at the first iteration, we get something that's basically still close to 0. And if we look at the data, so here's the data, these black dots, okay? And here's our predictions, right? So we're not even close. We're still the 0 model. We're predicting 0. Yeah, we're just not done. On this axis here, we're actually plotting phi d, so that's our misfit, as a function of iteration. So this whole procedure is going to go for 30 iterations. We're concentrating only on fitting the data. And so let's just see what happens. So let's try to fit the data better and better and better and see how we do. So let's go to another iteration. So this is iteration 6. Okay. So here's already, now we're starting to see something. So see it's sort of coming in there. We're starting to detect a bit of negative. The misfit, okay, we're obviously fitting the data better so we've got positive values up here, we've got values down here. And on our misfit function, we're down here with this green dot. Okay, a couple more iterations. Going. So this is starting to get not too bad, right? At iteration 12, we've got our predicted model. It's looking like this. So it's got a nice kind of dip in here. And as far as misfitting the data, well, we're actually getting pretty close, right? So not bad. But let's just now start to gradually see if we could do it better, right?
What's the red curve?
We'll come back to that.
Oh.
Yeah, there's quite a few things on here though. We'll come back. What I really want to do in here is just emphasize the point that if we're just thinking about the misfit, we can get into problems. Okay, so if we go to iteration 16, now that's fine, not too fast, Jeff. We go to iteration 16, now we can start to see we're doing a little bit even better at fitting the data. Here's our misfit that's down here. But we're actually changing the character a little bit. Keep going. So 17, 18, one more. Okay, now look to see what's happening. We're continually fitting the data better. But look at all this structure that's starting to come in. So we're fitting the data better, but from the point of view of recovering that model, we were actually better earlier on. And look to see what happens as we continue to do that. So let's keep going. So now here we are at iteration 20. Like, you know, we're continuing to reduce the misfit. Right? So we're getting better, but now look at the model. I mean, there's no real information there, and things just continue to get worse. 2, 3, you know, we're reducing the misfit, but at some point, all you're left with is junk, complete junk. So we can't do that. The fundamental aspect of the inverse problem is that you need to keep track of the uncertainties in the data. You don't want to overfit the data. You don't want to just be concerned about fitting the data, because otherwise you just, you know, the noise just creeps in and you end up getting all kinds of structure just by fitting the noise. So that's probably going to be a good place to leave it for lunch. The take-home message here, we're starting to kind of get the idea, like, okay, how we could do this, but and misfit is clearly going to be important, but we can't let it totally guide our analysis. So we'll leave that here at this point, and we'll pick that up then right after lunch. Thanks, that's great.